got a cone, and it's an inverted cone, or else it won't hold any water. And we've got this cone. I do not know any dimensions of this, so we're just getting a basic idea of what we're looking at. So I'm going to label this R, that's my radius. And then I'm going to have a water level in this cone. So, yeah, from here down, got water, I guess. So I've got a water level, so I'm going to label that H. I guess really, I really shouldn't put the R where I put it. Let's put R right here on the surface of the water. And does anybody remember volume of a cone formula? Do you remember volume of a cylinder? Or any, like prism, a cylinder, volume is going to equal the area of the base times the height, but for a cylinder, the base is a circle, so that is pi r squared times height. That's for a cylinder. So anytime you're doing, if you're finding the volume of any cylinder or like a rectangular prism or a triangular prism or any type of prism, it's always area of the base times the height. So if you have a triangle on the bottom, you'd find the area of that triangle and then multiply it by the height. Or if you have a rectangle on the bottom, you'd find the rectangle area of that rectangle, multiply by the height. With a cylinder, you got a circle on the bottom and you multiply by the height. Does anybody know how many times you have to fill up a cone in order for it to equal a cylinder? I'll give you. Let's just see. How many times are you going to fill up? So it's got the same base, same height. How many times does you have to fill up this? Or how many of these would you have to fill up this? Three. Each time you have to. So, no, it will take an extra to fill it up. But you, it takes 3 cones to equal a cylinder. Okay, so if you have the area for a cylinder, which is pi r squared times height, then volume is 1/3 of that. This is also why if you ever see anything in the grocery store or somewhere that's cone shaped, it is a scam to make you feel like there's more in that package than there really is. Because it takes 3 of these to equal 1 of these. But it looks sort of the same size. So, scam. Marketing. So, this is our volume formula right here. On the AP exam, they do not necessarily give you any formulas on the AP exam. You definitely do not have a formula sheet. And for some questions, they will give you the formula in the problem. So they might give you a question, and they might say the volume of the cone is given by 1/3 pi r squared times height. They might do that, but they don't always. So we generally need to know most volume formulas. So that's something that we will go over as we go through several different problems. So as we make a note of these, that might be one you want to kind of like box off, say, volume of a cone, and make sure that you know that one. To me, it always helps if you just think of your basis for this. Anytime, it's always the area of the base times the height. And so anything like this shape would be the area of the base times the height. We have this would be the area of the base times the height. And like two triangular prisms, area of the base times the height. So the formula changes based on what shape your base is, but it's always area of the base times the height. And then whenever you do a cone or a pyramid, it's a midterm. So a pyramid as well. So that's just to kind of help you remember those formulas. So what we're going to be looking at is we want to know the rate at which the volume is changing. So what we have to do here is we have to take the derivative of this equation. Okay? Because if we've got an equation for volume, if we want to find a rate of change for that, then we take the derivative of that formula. Now, we want to know, in most cases, we want to know the derivative with respect to time. Because as we watch the water leak out of this cone, then that is all transpiring at a certain time, right? The longer the water has been leaking, the lower the water level is going to get, the less water you have in the cone. So what we would do is we take this derivative with respect to t. Okay, so this is a little bit like our implicit differentiation. Implicit differentiation was like when I had x squared plus 3y equals 7, and I had 2x plus, and here I had to do 3 dy dx equals 0. So anytime we took a derivative of a y, we had to put dy dx. If it was an x, it was okay. So what we do here for related rates is we're going to take the derivative with respect to t. So that means when I take the derivative, I'm going to take the derivative of v, which would just be 1. But then with it, I would have to put dv over dt. Because I'm taking the derivative with respect to t. And so that is not the same variable as v, so I would have to put a dv dt with it. And then over here, I would have to take the derivative. 1/3 pi, that is just the coefficient, right? Is it okay with you guys if I write it as pi over 3? That'd be the same, right? Because it's like pi over 1. That is just the coefficient. I'm going to leave it out front so I don't have to mess with it. But for this part, I've got to take the derivative, r squared times h. Since I have two variables there, I have to use the product rule. So I would use the product rule to take that derivative there. I would say r squared times the derivative of h. Well, the derivative of h is just 1, except I've got to put dh dt with it. And then I would have plus h. Now I've got to take the derivative of r squared, which is 2r. But I took the derivative of a r, which is not a t, so I have to put dr dt with it. So it's a little bit like our implicit differentiation, except for you have got to put a d, h dt, r dt, dv dt, d whatever dt with everything you take the derivative of. Where it was only with the y's, since t is not a variable in our equation, we have to put that with everything we take the derivative of. So anytime we take a derivative of any variable, it's got to have this dh dt or dr dt or dv dt with it. So let's just talk this is not a problem that we've got to solve, but I just want to talk about what the different parts mean. Okay? So obviously for this one, r is radius of the water. Not the radius of the whole cone, but just the radius of the water, because that's what we're looking at here. The tank up here is empty. And h is our height of the water. Okay, so those are the same in the volume formula and in our derivative. So whenever we see dv dt, this is the rate that the volume is changing. Okay. When we see dh dt, this is the rate that the height is changing. Any guesses on the RDT? Good. Rate at which the radius is changing. It would be good if I had a cone I could actually fill up with water and we could watch this happen. Give me just a quick second. I feel like there's got to be a YouTube video of this cone. This is a very typical calculus problem. Let's see. Oh, here's one. Thanks. Oh, yeah. This is exactly what I want. So, I'm going to put the lights off real quick because it's not very bright. So, you've got a cone here. I wish it was a little bit brighter so that we could see it a little bit better. But the cone is filled with water up to the level right. Oh, I got this here. But so what we're gonna watch this video of it draining, and an exciting video right there. But what I want you to think about is how the height of the water is changing. Is it changing at a constant rate, going down the whole time, or does it start off really fast and get slower, or does it start off really slow and get faster? So let's watch and see what happens. Okay, so especially there at the end, you can see, is it going down at the same rate the whole time? It is not. Is it possibility of something that could happen here? So we are not going to do this problem, nor will we ever get quite good enough to do this problem because it's a pretty difficult problem. So if you had a swimming pool shaped like the one below, this is a pretty typical swimming pool shape with a shallow end and a deep end. If you wanted to make it more complicated, sometimes like the sides are sort of tapered down as well, which could make it even more complicated. And it has a leak that is causing the height of the water to drop 1 inch per day. Once the leak is discovered, the lifeguard starts filling the pool with a water hose that adds 6 gallons per minute to the pool. How long will it take for the pool to drain or overflow? Assume that a heavy rain has just came that filled the pool all the way up to the very top. Also assume it does not rain anymore until the pool is either drained or overflowed. So what's happening here is you're draining this pool at a rate of 1 inch per day, and you are adding water to the pool at a rate of 6 gallons per minute. And so what you really need to know is that are you adding water more quickly than it's draining, or are you draining it more quickly than it's adding it? Because unless they're exactly the same, the pool is either going to eventually overflow because you're putting more water in it than is draining out, or the pool is going to drain all the way completely because you're not putting in as much water as is draining out. Now, you should probably try to get your pool fixed if this is happening. I do realize that, but this is a temporary fix. We want to know whether or not the pool is going to overflow or is going to drain out. So there's a lot of variables. First, you would have to start off by finding an equation for the volume of this pool. And the top part of the pool would be easier because it's just a rectangle. But then you've got this other area of the pool down here at the bottom, which is going to be more difficult to find. You also would have to know you've got a lot of unit problems because you know the height is changing at 1 inch per day. This is measured in feet, so you would have to convert something there. You also know you're adding 6 gallons to the pool per minute, but we're talking about like cubic feet of pool area, so you'd have to change gallons to cubic feet. There are a lot of factors that would have to go into figuring out the answer to this problem. The other question might be, where is the leak at? Because if the leak is over here in the shallow end, the pool's never going to drain completely because it's going to stop draining if the leak's over here. Whereas if the leak is in the deep end, it's going to drain completely. You also would consider the height is going to change at a constant rate here, but then once it gets to the deep end, it's not going to change at the same rate anymore because your volume is different. So there's a lot of different factors that you could look at there and consider. Obviously, if you're the lifeguard at the pool, I realize you're not going to break out your calculus to figure all of these things out. But we could also, I just went with the swimming pool because it's easy for us to picture and think about what is happening. We could also consider things like if we had oil coming in off of the pipeline, and we've got a tank that we're using this oil for, but we are draining not necessarily draining the oil, but you're using oil at a certain rate, but you're also adding oil at a certain rate from the pipeline. You would need to know, when is this container going to reach its capacity? So all of those things are things that you might need to consider for something like this. So this is the idea of what we're getting to. We won't ever quite get to the point where we could do this problem. We are not going to get to the point where we are going to do this problem. How about that? Because you're talking about a problem that would take class periods to do, probably. So there's a lot of factors going on there. Today, we're going to do naked problems. So these problems don't have any context of anything with them. And we need to learn how to do those first before we can do the ones that are in context. So, whereas on these problems you would have to come up with a volume formula and then plug a lot of different things in, these problems that we're going to do today, they already give you the formula. So this would be like if this was your volume formula. So we are given y equals x squared plus 3, and it tells us to find dy dt when x equals 1 if dx dt equals 2 when x equals 1. Okay, so what we're going to do every time is we're going to start with our equation y equals x squared plus 3. And we are going to take the derivative of this with respect to t, which means when I take the derivative of y, which is just 1, I have to put a dy dt with it. And when I take the derivative of x squared, I have to do 2x, but then I also have to put dx dt with it. And then, of course, our derivative of plus 3 is 0, so we don't really include that. And so we are looking for dy dt. So that is what I'm trying to solve for. You're never going to plug a number in for whatever you're trying to find. So if we're looking for dy dt, we're not replacing that. Just can't solve for it if we replace it with a number. And then basically you're using the information that's given to you to plug into this equation. So I see that x equals 1. So right here, I'm going to plug in 1. And then I know dx dt equals 2 when x equals 1. So this rate of change, this dx dt, it might be changing, but at x equals 1, which is what I'm concerned with, it equals 2. So I would take 2 and I'd plug it in for dx dt. So it really is a very simple problem for this. You just have 2 times 2. I'm sorry, that's 1 right there. 2 times 1 times 2, which is 4. This problem's going to have no units. It has no context. We don't know what y is, what x is, why it's changing like that, but we know dy dt equals 4 when x equals 1. So the rate at which y is changing with respect to time is 4 whenever x is 1. So once we get into context, you're going to have to come up with your own equation. It'll be a little harder to figure out where to plug in the numbers, but the principle is the same. You're going to have an equation. You're going to take its derivative. You're going to plug in the information that's given you to solve. So that's the idea. Let's look at the second one. We've got x squared plus y squared equals 16. We need dx dt when x equals 4 if dy dt equals 3 when x equals 4. So we'll do the same thing we did for the last problem. So we'll take our derivative. When we take our derivative, we'll have 2x dx dt plus 2y dy dt. And then the derivative of 16 is just 0. And then we got to know our information that we can plug in, and we also want to know what we're finding. So dy dt is what we're finding. So dy dt, I'm not going to plug a number in for dy dt. It is, thank you. I don't know why I said dy dt. I'm losing my mind. Okay, dx dt. So we will not plug in a number for dx dt. But that means we got to plug a number in for x, y, and dy dt, or else we can't solve it. So I see my x right here. That goes here. And when x is 4, I know dy dt, that goes here. And so if I plug that stuff in, I've got 2 times 4 dx dt plus, we've got a problem here because I want to find dx dt, but I don't know why. It did not tell me why. So any ideas of how we could find y? You could. And since we know x equals 4, we can plug that in there. So the original equation, if I know an x value and I plug it in, it gives me the y value, right? So I'm going to go back up here, and I'm going to take this 4 and I'm going to put it into the original equation. So 4 squared plus y squared has to equal 16. So 16 plus y squared equals 16. So I'm going to subtract my 16. What does y have to be? Y equals 0. So right here for that y that I could not find earlier, now I'm going to put a 0. So that gives me 8 dx dt. That's just 0 right there, so this equals 0. And we'll divide by 8. So dx dt also equals 0. Okay, questions? Okay, here's our next one. Our equation's much more complicated on this one. 2xy plus y squared equals 8x. So, but our process is the same. We take our equation, we find the derivative. Okay, so for the derivative, what have I got to use to take the derivative of this first part? Product rule. So I'll have 2x times the derivative of y, which is dy dt, plus y times the derivative of 2x, which is 2 dx dt, plus y squared. I'm going to have 2y dy dt equals 8 dx dt. So I need dy dt, so I'm not going to plug anything in for my dy dt, which I actually have 2 of here. I do know that my y is 1, so those y's right there are going to become 1. I know that my dx dt is 5, so dx dt is 5. Do we have any variables that we're not going to be able to plug in right yet? That x right there. So since we can't plug that x in, we need to find x. How are we going to find x? Original equation. So we'll have 2x times 1 plus 1 squared equals 8x. So that's 2x plus 1 equals 8x. We will subtract that 2x. 1 equals 6x. And then we'll divide by 6. So x equals 1 over 6. Any questions so far? Okay, we're going to plug everything in. So we'll have 2 times 1/6 times dy dt. We don't want to replace dy dt. That's what we're finding. Plus 1 times 2 times dx dt, which is 5, plus 2 times 1 times dy dt. We don't want to replace it, equals 8 times dx dt, which is 5. And so we get 1/3 dy dt plus 10 plus 2 dy dt equals 40. I could subtract this 10 over here, and then at the same time I need to put my dy dt's together. So 2 plus 1/3 is going to be 6 over 3 plus 1/3, which will give me 7 over 3. So I'll have 7/3 dy dt equals 30. And then I need to divide by 7/3, or dividing fractions is easy as pie, flip the second and multiply. So I could just go ahead and multiply by 3 over 7. So for dy dt, we end up with 90 over 7. Okay, questions? All right, I do want us to do one problem that's in context. So in a rectangle, the length is 8 feet longer than the width. The length of the rectangle is changing. When L equals 5 feet, the LDT equals 5 feet per second. Find the rate at which the area is changing when L equals 5 feet. Okay, I like to draw myself a picture for these. So, got a rectangle. The length is 8 feet longer than the width. So, this is length and this is width. Then I know that the length is 8 feet longer than the width. So, I could take the width, add 8, that gives me the length. Now, what's sometimes difficult is even knowing what formula you even need to be trying to take the derivative of. So you need to ask yourself, what rate are we trying to find? So we're trying to find the rate at which what is changing. The area, right? So area of this rectangle, area equals length times width. However, if I do length times width, then that means I'm going to have a variable w. And if I have that variable w, do I know what w is? At any point, I do not. Do I know dw dt? I do not. So I really need this formula to be in terms of L. So I need all L's here. So it would be easier actually to change to W's, but I don't have dw dt. So if I want this in terms of L, I could subtract this 8 right here. So L minus 8 equals W. And this is always the same because it says a rectangle is in a rectangle, length is 8 feet longer than the width. So if I want to, I can write this formula as L times L minus 8. I can just take what I found here and replace my W. And I'm gonna back up here and say I could have taken dA dt. Don't write this down because it's wrong. And I could have found the derivative of this, which would be L times dW dt plus W times dL dt. But if I do that, that gives me this dW dt that I have no way of finding. I guess I could find W, but I can't find dW dt. So it's just really not the best idea. If we can get it, a lot of times for these problems, if we can get them in terms of all one variable, it makes it easier to do. So I'm going to go ahead and distribute that L. So my area formula is L squared minus 8L. Okay, so I'm going to take the derivative of this with respect to t. So whenever I do that, Justice, what will I get for my derivative when I take the derivative of a equals L squared minus 8L with respect to t? Almost. Anytime you take the derivative of any letter, you have to put dL dt minus 8, and then you'll have dL dt, that one as well. And over here we have dA dt. So any letter that you take the derivative of, you got to put that letter d, that letter over dt for d. Okay, so they told us L is 5, the L dt is 5. So we would have our dA dt would be 2 times 5 times 5 minus 8 times 5, which is going to give us 50 minus 40, which is going to be 10 is our dA dt when L equals 5. Now, I do need to use units for this. I think, yes, they gave us the length is in feet and the rate is in feet per second. So dA dt tells dA dt is the rate at which area is changing. How do we measure area for this problem? So if I have, let's just make one up. If I have a width of 2 and a length of 10, what's the area, or 2 feet and 10 feet? What's the area of that rectangle? 20 what? Feet squared. Right, so area in this particular case is going to be measured in feet squared, but this is the rate that is changing, so it's going to be feet squared per second. Okay, so at that point, whenever L equals 5, the area is increasing at a rate of 10 feet per second. It will not always be increasing at that same rate, because if we think about, even if the L is increasing at the same rate, then here we could have this one would be 2, 2 and 10, which gives an area of 20. So the next box might be 3 and 11, which gives us 33 feet squared, and the next one would be 12 and 4, which would give us 48. You see that area, like here it went up by 13, then it went up by 15, the next one's probably going to go up by 17. It's not increasing at a constant rate. Even though the length is increasing constantly, the area is not going to increase at that same rate. Which is going to be the case anytime you have like a unit squared or volume or anything like that. Okay, questions? Now, I just wanted to get to that one because I wanted us to see a little bit of the application. Of course, that is an oversimplified situation that is still not very real life. I promise we'll get to some that are a little bit more real life. But tonight's homework is not very real life at all. Tonight's homework, you're going to do page 194. You're going to do 1 through 4 and then 5 through 8. But for 5 through 8, only do part A for each one. All of these are your naked problems where you just have X's and Y's.